Okay, we're gonna get started. If you guys can give a big warm welcome to Bret, that would be great.
Cool. All right. Howdy. My name is Bret McGowen. I'm a developer advocate at Google on the Google Cloud Platform team. You can follow me on Twitter at BretMCG. Some things about me. So I live in New York. I am an aspiring Node developer. It's going okay. Again, you can follow me on Twitter at BretMCG. Even though I live in New York, I have to tell you, I'm from Texas. Let's fix this picture.
Sorry.
There we go.
How can you tell someone's from Texas? Don't worry, they always tell you. So, howdy and welcome, I'm required. So we're gonna talk a little bit about machine learning. So just actually a quick question, who is this their first DevFest? Okay, awesome, super cool. Good, because I'm gonna reuse some slides from last year, so it'll be new. So machine learning, and Sarah talked a little bit about this morning in the keynote, but I'm gonna do kind of an interactive exercise. So machine learning is using examples to answer questions. So let's try a traditional way of doing image detection without machine learning. So in a traditional way, you would like write rules to see what an image is, for example. So here's the example. I wanna write some code, quote unquote, to figure out the difference between an apple and an orange. So what are some like programmatic rules? Like what are some things I could look for in the photo? These look exactly the same to you? Is that the projector? Color. So color is a great one. Anything else? Stem, shape. Texture is a great one. So these are all great examples. So let's say we chose the easiest one, which was color. So we just look through the picture, we count out the number of red pixels, we'll count up the number of orange pixels. If it's more red than orange, it's probably an apple. If it's more orange than red, it's probably an orange. But immediately we run into a problem, because now we're gonna get another question. Which one of these is an apple, and which one of these is an orange? So now we have to go to the next one, which was, does it have like texture or stem? Okay, so the apple clearly has a stem. But then maybe we get this set of images. And one has a stem and one doesn't, but the texture of that orange is very different than the texture of the previous orange. So the point here is that right away, your rules start to fall apart. They become fragile because there'll always be these sort of edge cases, these corner cases that don't address the rules that you have in place. And moreover, if someone now says, and also, I want you to tell the difference between an apple, an orange, and a pear, well, we have to start all over again, because we have a system that's really good at telling the difference between a red apple and an orange orange. But what about a green apple and a green pear? They both have stems, they have similar texture, they have similar shine, they have similar color. So that's where machine learning comes in. And what you do is, oops, let me back up. Let's actually try another example, because it's deceptive. And I get asked a lot, machine learning is hard, writing TensorFlow code is hard, is it always necessary? So let's take an example where maybe you don't actually need to use machine learning, right? So that was an apple and orange, and that's kind of a tricky example because they're similar in a lot of ways. So let's take those two things that are not at all the same. Let's take a dog and like a cupcake. So let's play this game again. What are the differences between these two images? Nothing. Wow, okay. I agree, these look exactly the same. No, any ideas? Texture. Depth of field. All right, we're getting like some advanced photography in here. Eyeballs. I hope there's no eyeballs on your cupcakes. Fur. Yeah, well, there's actually a deli by my apartment that would beg to differ. There's regularly fur on those muffins, but yeah. So this is actually these are pretty obvious examples where you probably would never get confused between, let's say, a puppy and a muffin, right? Who needs machine learning? Similarly, what about like a dog and a mop? Clearly, two things that are super easy to tell apart. Most of the time. Actually, there's a couple of these that I'm actually still not sure what it is. Sloth or croissant. I could do this all day. But you get the point. By the way, we ran these images through the Cloud Vision API, and it was able to figure out, like, at least for the puppies and the muffins, it got them all right, which is pretty good. It didn't used to. So machine learning. We use it a lot at Google. We use it not only to tell the difference between apples and oranges and pears and things like Google Photos, but also in things like self-driving cars, because it's pretty important that you tell the difference between, let's say, a red light and a green light, or a pedestrian and a traffic cone. One thing is okay to hit, the other is not. So we use it. And so how it works is you basically take a ton of example images. So a ton of pictures of apples, a ton of pictures of oranges, like hundreds or thousands. And the system just looks at those and learns on its own sort of what these rules are in these edge cases. And it turns out to be, with enough data, more robust than writing those hard-coded rules yourself, which are very fragile and aren't general purpose. So that's how kind of machine learning works in general, and at Google, we trained on a bunch of examples. So I wrote a little demo here where I have a system that will tell, basically I've got these handwritten digits. If you've done any machine learning, you'll know this is it's called the MNIST data set. It's basically the hello world of machine learning. So it's not a complicated. There's plenty of tutorials if you want to write this code on your own. But you have these handwritten digits, and I'm going to use machine learning to figure out what the digit is, right? So for example, I'll drop in a 2. Oops. I'll drop in a 2. I'll drop in a 2, and this awesome little headshot of mine shows up. Don't know what that is. Let's try that again. Okay. I don't know why this little UI there we go. Whatever. Well, that's awkward. So I was able to tell the 2. Let's try 5. Let's try 0, rather. That's the one I clicked on. So it's pretty good at telling 0, 5, and then finally, let's do, what's this last one? 7. So you see it got them all. Oh, it didn't. Well, this is embarrassing. I worked really hard on this demo, and I really wanted it to be flawless for y'all here at DevFest Twin Cities. So I don't know what to do. I'm probably going to get fired for this because this is humiliating. I'm showing off Google machine learning, and it crashed catastrophically in front of you on stage. But I guess what I could do is actually train the system live in front of you so to not only recognize digits 0, 1, 2, 3, 4, 5, 6, but also what I forgot to train it on, which is digits 7, 8, and 9. So by actually updating the training set and fixing the demo, I can illustrate the point I'm trying to make in this talk. So it's a pretty convenient mistake that I made. So what I'm going to do is I'm going to kick this off, and then, let me minimize that. I'm going to kick off this training job. That is so, can we get this? It's getting creepy. All right. Nope. Well, little Bret is going to be watching you the rest of this demo. Cool. So I am going to load digits 7, 8, and 9. And by load, what I mean is, let's tab over here. So I've got like a ton of examples of 7s. So, and you can see people have like crazy handwriting. Like, what the heck is that? Like, that's definitely the Loch Ness Monster. There's a boomerang. Like, come on, people, get it together. But there's like hundreds of these 7s. And I'm basically just dropping them in to train the system. So you can see now this process. It is recognized the 7s, 8s, and 9s that I just uploaded. It's doing some data, and I'm going to get into detail in the rest of this talk. And it's doing some training, just like Rocky here. So hopefully by the end of this talk, that will be updated. All right. So let's get back here. So again, to recap, it was able to recognize, for example, 0, 2, 5, but it was not able to recognize 7. It was such a shocking error that I made in my demo. It's a good thing I had a slide that showed what that error was going to be, recognizing a 7 as a 0. So hopefully by the end, it will actually be able to recognize a 7, and I'll walk you through how that worked. So the short version is training new models today is complicated and manual. So by training new models, I mean ingesting all this new data and updating your machine learning models. What we want to do is just add the files. So literally, I did it in the command line, but essentially what I did is I just dumped a whole bunch of 7s, a whole bunch of 8s, and a whole bunch of 9s into this file storage bucket, and we want to just automatically update the training model. That is the dream. That is the goal by the end of this. So don't do this, number one. When we were putting this demo together, did everyone see Sarah's keynote this morning, which talked about AutoML? Right. So AutoML did not exist when we built this demo, and we knew they were working on it. So essentially what we're doing is making a really crappy version of AutoML. But it's okay because the principles are the same, and if you're using image data, use AutoML if it makes sense. But a lot of times we're actually not working with image data. We're doing machine learning on things like a recommendation engine, right? So you're dumping in all this data that's like who my users are, their demographics, where they are, what they've spent their money on previously, and we want to intelligently make recommendations, and we're going to use machine learning to do that. So normally your data is actually like more database oriented, like rows and columns, than in images. We just made an image one because we thought it would look better, but if you are doing image training, use AutoML if applicable. So that's don't do this, number one. All right, so here's how the machine learning workflow works now. So you take your data, you process it, you manipulate it, you clean it up, you get it into the right format for your training, you're gonna store that data somewhere. Then you're gonna take sort of this new round of data, so in this case, the 7s, 8s, and 9s, like new data we wanna train on, and we're gonna use that to update our model. And then we're gonna deploy that new model, so once we do what we call prediction, when you upload that handwritten thing, it's gonna do a prediction what it thinks that is. So you deploy the new model that now incorporates that new data, the data that has been trained on 7s, 8s, and 9s. So people have asked me, we're about to get into the sort of serverless side of things. Does this change how I write my machine learning code? And the answer is generally no. So as you're working through your machine learning, and this is not a TensorFlow talk, so I'm not gonna get into like too much depth. I'll show you a little bit of TensorFlow, but I'm not gonna get into too much depth about the ML side of it, the actual code writing. Do it locally, right? Like you do it on your workstation, train on a few images, see how it goes, and iterate. What I'm gonna walk you through is, once this is like out for real, how can you have your model automatically updating and improving in production on an ongoing basis? So to kind of get that first crack at your algorithm as you're tweaking all your classifiers and things, do that locally, do it on your workstation. To do it all in the cloud might be a huge pain. All right, so what are we gonna use for machine learning? I kind of already mentioned it, but we're going to use TensorFlow. Has anyone not heard of TensorFlow? It's okay. I feel like that was not a good way to phrase that. If you haven't heard of TensorFlow, let me give you the quick overview. It's basically an open source library based on some ML libraries internally at Google that we open source to just like move the ML community forward. I'm not going to get into a lot of TensorFlow. If you're curious what the name is, tensor is a multi-dimensional array, and a flow is a graph of operations. For example, you could have a 3 and a 2 that flow into a plus operation, and then the result is a 5. All right, so let me just show you a little bit what the TensorFlow code looks like. Like I said, I'm not going to get in too deep on it, but just to show you what we're doing. So what I have here is a Jupyter notebook. This is all Python. Let me clean up my previous thing. So just to kind of briefly walk through, I'm going to import the TensorFlow library, just some logging stuff. I'm going to output the version, 1.4. I think it's 1.6 now. All right, I'm going to ingest the data set. So this is like the images. Let me back up for a second. The code that I'm walking through is the code that is running to do the training in the cloud. So it was developed, again, locally. So I have an input function. Again, I'm not going to get into the details. Batch size is like how many things to process at a time. Epochs is like how many times you process the whole data set. Do you want to shuffle it or not? So again, these are all things that you want to tweak to see how your model is doing, and you want to do that locally as you're developing it, not like in production. Feature columns, I'll get into this a little bit later graphically, but feature columns is like, what are the things that you're tracking to do your prediction? So in the case of, say, demographics, like census data, so where the person is located, how old they are, what their education level is, whatever the census tracks, like each one of those would be a feature and has some either set of discrete values or like a range of values. And then classifier, so here is linear classifier, which is essentially the simplest one, and it should start outputting some results, maybe. Oh, I haven't trained it yet. So I'm going to train it, and then we're going to evaluate it. So just briefly, what it's doing is we're training it on a bunch of images, and then we evaluate it. And the way we test our model to see how good it is we don't train it on all the examples we have. We actually keep some out, and we don't show it to the model. But these are things we know the answer to. So in the case of the images, like we know some weird 7s and some weird 8s or whatever, but we don't show it when we train the model. That way, when we then we ask the model to evaluate what we've trained on, And then depending what percentage correct it is, we know how good our model is. Does that make sense? It's sort of like, it's like a test, right? You get homework problems which are very similar, but generally speaking, your teacher doesn't give you the test problems to do. This is the first time you see it is during the test. So here we can see, if I scroll down, you can see that our accuracy is 92%, which seems pretty good. So now we're going to do what we call a deep classifier, this deep neural network classifier. And let's do the same thing. We're going to run it and check our accuracy. So what was the other one? Is 92.3% accurate. So let's see if this one does any better. Live scrolling, yes. There we go. So 95.8, roughly 96. So it was improved. So that's good. So now what we're actually going to do is sort of visualize some subset so that we can see how well it's doing. So this was the linear classifier. This is the simpler classifier. So it's expecting 39984, and it got 58984. So not super great. It got 3 out of 5. Let's see how our deep classifier did. So we're expecting 39984, and the deep classifier actually got that. So you can see, even though it doesn't seem like 92 versus 96% is a lot, it actually manifested itself pretty obviously. And then just visually, if you want to see the data that we just tested on, again, it's looking for a 3. That's clearly a 3. It's looking for a 9. That's clearly a 9. 8 and 4. So cool. All right, just curious. Let's check over here. All right, so it is actually done training. But we won't play with it just quite yet. So TensorFlow, just generally speaking, supports many platforms: CPU, GPU, TPU. TPU is like a specialized hardware we have in Google Cloud. It also supports Android and iOS. So there's a couple of use cases, and Raspberry Pi, a couple of use cases I want to talk about. One is you can train your model and do prediction in the cloud, which is what we're going to do as part of this demo. But you also can train your model, package it up, and then deploy it to your Android or your iOS device. So you actually can do prediction on device without having to ever connect to the internet. So if you think about like real-time image recognition, like if I want to be able to hold up my phone and have it recognize things right away without the latency of sort of capturing an image, uploading to the cloud, doing the processing, and coming back down, you can actually pre-train your models and then deploy it to your Android or your iOS device. Super cool. I think you can train on your device, but you probably don't want to because it's going to burn your user's battery to the ground. So anyway, so train in the cloud. You can predict in the cloud, or you can predict locally on device. Where do we run our TensorFlow code? We're going to run it in Cloud Machine Learning Engine. I think Sarah went into this a bit this morning in the keynote. But we're going to use this. So we're going to use this both for the training and then for the prediction, because ML Engine can do both. And sort of the first introduction to the serverless part of it, it all, I'm jumping ahead of myself, but it all instantly spins up when you need it and shuts down when you don't, which is really, really cool. So what do we need from like a cloud perspective to put this all together? So we need some kind of file storage, we need a database, and we need some machine learning. And traditionally, these are all things that like a DevOps person has to manage. Like someone has to be in charge of making sure your disks aren't going bad and doing redundancy. Someone has to be a DBA and manage your database and shard it and scale it and replicate it and back it up. And then for machine learning, you have to have some cluster of machines that are running TensorFlow to do all the training and do the prediction. But luckily, we can go serverless. So if you don't know the term serverless, very briefly, it has some characteristics, one of which is you don't manage any servers. You just sort of consume it. You're not aware, like, how many machines did it take? I have no idea. Maybe it was 1, maybe it was 100. You only sort of pay when you are directly using it, so you don't really care. Automatic scaling, it similarly scales up and it scales down. And by scaling down, you only pay for what you use. So in this case, if you're not actually actively training or actively doing prediction, your cost is 0. Well, there's like a storage cost if you're storing a bunch of images, but in general, you don't pay anything. And then the instant you want to do some training, or the instant you want to do some prediction, it spins up all the resources you need, does what you need, and then spins it back down. So that's sort of the serverless dream. That's why it's, I think, kind of fundamentally different even than a lot of normal cloud computing, where a lot of times cloud computing looks a lot like it looked in a data center that you owned or at a server in your closet, where you just had stuff that was just running all the time, whether it's actually doing anything useful or not. And then the fourth thing is event-driven. So this is particular with we call functions as a service. And event-driven means a couple of things. It means something happens, triggers another thing. So what ends up happening is you end up with these event-driven architecture diagrams that I feel like look a lot like either dominoes or like the old-timey fireman's bucket brigade, right? So the fireman doesn't like get the water and then like walk it all the way over to the fire. And so there's like a row of firemen and you would just like hand one to the next. And it's much more efficient. So this, in this case, some event happens in the cloud. So in this case, a 7 or 600 7s are dropped into file storage, and it sets off this chain of events, which we'll get into in a second. Which means a lot of times the architecture diagrams look like this, which can be really scary, but welcome to microservices, y'all. It, for me anyway, takes a while to like, whoa, this is a good thing, I promise. It just means every little piece of this is independently contained and managed and scaled. But when you see it sort of from the architecture perspective, it can be overwhelming. So when we see this particular one, don't be alarmed, it's okay. So the specific Google Cloud tech that I'm going to use for storage, for databases, and for machine learning, cloud storage, it's just our binary file storage system for Google Cloud. It can store massive terabyte-sized files. BigQuery can query terabytes or even petabytes of data just using regular SQL. And generally speaking, when you talk about machine learning, the more data, the better. So that's not always the case, but generally the more data you train on, the better and the more accurate your result is going to be. And BigQuery can scale, like I said, to petabytes of data. So this is a really good use case. And it's serverless, so when you're not actually querying something, it doesn't cost you anything other than storage, which is really nice. And then we're going to use something to staple these all together. Something very near and dear to my heart is called Cloud Functions. It is so near and dear to my heart. I have a bunch of Cloud Functions stickers, so find me afterwards, and I'll get you one. So we're going to use Cloud Functions to sort of be the glue that puts all of these pieces together. And I think it'll make more sense once we get into the diagram. All right, so phase 1, training. So this was the process by which when I dropped the 7s, the 8s, and 9s into cloud storage, it started the training process. The Rocky GIF is not actually normally part of it. I added that, just so you know. So this is going to look familiar. This is sort of the general steps to machine learning. First, we need to process the data. We need to save it to the database. We need to batch the new data, so like just the 7s, 8s, and 9s, and then use that for training and then deploy that model. And let's dig a little bit deeper into what that looks like. So the first thing we do, drop a bunch of images into cloud storage. So in this case, I think it was like 600 or 700, let's say 7s. Every single time a file gets dropped into cloud storage, it's going to spin up a cloud function to do something with that file. So if you think about like how much of a pain in the butt it would be to manage that yourself, like you need to go from having 0 files being worked on to 700 in like a couple of seconds. That is like a really good use case for serverless because you're not paying for anything until it's literally spinning up, does whatever processing, and then spins down. So what processing are we doing on the images? So this brings us to the second, don't do this. The first one was for training images, use AutoML if you can. It's in private alpha, so if you can't get access to it, then maybe this is the next best thing. But the processing we're about to do is a little silly for our use case, and I'll explain why. It's because TensorFlow actually understands images. But what we're going to do is turn it into columns in a database. Because if you're not doing image data, you probably are doing it on data that is like columnar, like I was talking about census data. I keep going back to the census example, like where is the user located? How old are they? What's their education level? Things like that. So those are columns in a database. So that's probably, or there's a good chance that's what your data is going to look like. So to help illustrate that, we're just going to turn an image into columns. So what we're going to do, kind of ridiculous, but it works. We are going to actually turn all of the pixels into grayscale values. So we're going to have 784 columns so if you go from top row from left to right, the very first pixel on the top left, that is column 0. The second pixel is column 1, and so on. And then once you get to the end of that row, the next one, that's going to start column 29, and so forth. Does that make sense? So we're basically flattening this image into one huge long list of integers, which represents a grayscale. So 0 would be black, 255 would be white. So again, you would not actually do this, but this is to get data in a table format, so that I think hopefully it relates a little bit more. All right, so here's the pipeline. And to make this a little bit digestible, so we don't have this tons of boxes and arrows thrown at you, to make this a little bit digestible, I've sort of like labeled these. So the first thing we need to do is pre-process, which is kind of what we just talked about. So this is taking an image and then turning it into columns in a database. For you, this might be like normalizing your data. It might be doing things like checking. So for like location, sometimes people abbreviate cities, or whatever sort of data cleanup you might need to do to get things in like a nice, consistent format. And then we're going to save it to the database, and in this case, the BigQuery database. Then what we're going to do is we're going to take that batch, that new data, so in this case, the 7s, the 8s, and the 9s. We're going to extract that, because now we have a database that has all the digits that we've trained it on, but we don't necessarily want to pull out our whole data set every time and retrain on. You can, and actually we are, but we're just training like on top of the existing model. We're not like extracting it all from the database all over again. So then what we do is, on a timer, we just say, hey, give me all the new data that like I haven't trained on yet. So again, so I think in like an e-commerce context, if you want to update your prediction engine or like a song recommendation engine, and maybe just every day you just want it to get better based on the previous day's data. You want to improve it every day or every week. So this is where would be your timer. So every day, pull out all the new data that came from the last day, batch it up, and put it in a CSV. CSV feels a little silly, but believe it or not, that is the de facto like machine learning data scientist data format. So we go from a cool, like hyperscale, mega advanced SQL database to CSV. Welcome to 2018. But turning it to a CSV has a nice advantage, because as we drop it into cloud storage, it's going to automatically trigger the next step in the chain. So again, so we have the very initial 2, which triggers a function to turn it into database columns. We have a timer that then pulls out the new data, writes it to a file. Then that file write is going to trigger a next link in the chain. So again, think about the bucket brigade handing the bucket off from one user to the other. This cloud function then is going to take that CSV, hand it off to TensorFlow in Cloud ML Engine to update its model. So at this point in this diagram, we have now finished updating the model, and all we need to do is just push it to ML Engine and say, hey, use this model now instead of the old one. And again, we do this just with a file write. So it writes, it's literally it's a .pb file. So we just look for this saved model.pb. When that gets written, it triggers another cloud function. The cloud function says, aha, I have a new model. I'm going to tell Cloud ML Engine to use this updated model instead of the old one. So again, you can see it's like kind of a long chain of events, but each piece is sort of nicely self-contained and independent. All right, the version without the boxes. Process the data, save it to a database in columns, pull it out of an awesome database and put it into a weird CSV, train on that new data, and then deploy it so that when it does predictions, it has the updated model. All right, so now that we have that, we have the next phase, which is how do we actually use the new version of the new model. So here we have this 7, for example. We can, which I will, just drop it into cloud storage directly, which is going to call a cloud function to call Cloud ML Engine, and hopefully it will produce a 7. But one thing that's nice about cloud functions, not only can they be triggered off of events, like for example a file write to cloud storage, but you can also expose them as HTTP. So you actually could create an API through cloud functions that now anyone could submit an image and get back some kind of response. And in fact, this might be a really common use. Even if it's just other people in your organization or in your project, it's nice to give them a nice HTTP like REST API that they can consume, and cloud functions makes it super easy. All right, so here's the moment of truth. Am I going to get fired for failing my demo? I hope not, but we will see. So let's try this again. Because we saw, yeah, that it was all done training. It trained here on these 7s, these 8s, and 9s. We dumped them into cloud storage. It spun up literally a couple thousand cloud functions that turned these into columns, inserted it into BigQuery. On a timer, we took the data out of BigQuery, turned it into a CSV, and then trained on that new data, and now it is ready to be deployed. All right, so moment of truth. Will I be here next year, or will I be out on the street? All right, replace it. That's okay, it's accepted. I'm replacing it, and yes. All right, it now understands 7s. So super cool. No applause? Did you want me to get fired? I'm kidding. All right, so we didn't really get into too much of the actual machine learning part of this. So my teammate Yufeng And I put this demo together to kind of walk through how you can use serverless to improve your machine learning process. To actually get into the ML itself, he has a great video series called Cloud AI Adventures, and here's a bit.ly link. And it goes all the way from just very high, first couple videos are really high level, like what are the concepts, like what does training mean, what are some of the the things I talked about, like classifiers, just a really nice digestible way of learning about ML. And then as it progresses, it'll take you deeper and deeper into actually like how do you configure your Python environment on your desktop to what math libraries should you use, or what are the trade-offs when you're writing your ML code. So this is actually mostly how I've learned ML is from his videos, so I definitely encourage you to check them out. They're pretty bite-sized. They're anywhere from like 4 to 7 minutes each, so it's like not like a huge commitment of time to watch each one. And with that, here's a couple of links, other links, including his Cloud AI Adventures there at the bottom. That's a picture of Yufeng at the top. So if you have any ML questions, just tweet him. Don't get me involved. No, I'm just kidding. I'm the serverless guy, not the ML guy. So if you have questions about serverless, I can talk to you all day. If you have ML questions, we can find you. I think Sarah's probably around, can answer some of those, or I can get you the right answer if I can't answer it directly. Links to TensorFlow and Google Cloud Functions. So with that, thank you, and I'll take some questions. Yep.
I'm sure it's not terribly important, but was there a reason why you were using like negative colors for your numbers? So
So the actual answer to that is that, so MNIST is this like, as I said, sort of like the hello world of machine learning. It's this handwriting example, and just the MNIST data set is white on black. I'm not entirely sure why. That's just how it came, and I didn't want to muck with it, so. Yeah, so it's interesting because it's actually, it gives you a sense of how fragile this ML stuff can be, because if you invert the colors, it doesn't recognize anything. If you use like purple instead of white, it doesn't recognize anything. And that's where the lesson is, the data that you train on has to represent and has to look like what you're going to predict. Because to us as humans, we make this like cognitive jump that a lot of times we're not even aware of, that maybe a white 0 on a black background to us looks basically the same as a white 0 on a navy background, but to the computer it's not. Like, it's never seen a navy color before, for example. So it's important to make sure that the data that you get is representative of what like you're gonna see in the field. So, yeah. Yep. So I don't think it starts completely from scratch, but it does reincorporate all the existing data. So the problem is, and there's something called, I think, online training, which we didn't do, where I think you can sort of incrementally improve your model. But the problem is if you just said like, okay, just do another round of training with just 7s, 8s, and 9s, TensorFlow is gonna think like, oh, wow, the universe of numbers, like, pretty much just all looks like 7, 8s, and 9s. So you wanna train it on like a representative universe of data. So even though it would still be able to recognize, like if you just did another layer on top, it would still be able to recognize 0 through 6. It's way less likely to, because you just showed it a representative of the universe that only has 7s, 8s, and 9s, so it's gonna be like really unlikely. It thinks like, oh, I guess those other digits like just don't really exist anymore. So it kind of knows about them a little bit, but yeah, so that is a high level, but yeah. We essentially just keep that data. So storage is cheap in a cloud world, so we just keep it there and we just retrain. We just don't re-extract it from the database every time. We just keep it like in storage. Yeah, there may be a better way to do that. I don't know if like any ML experts wants to chime in, but yeah. Yep.
Are there any tools that help you, let's say you've got massive amounts of data in terms of inference results, that help you turn that back into additive training information?
Do you have an example you're thinking of?
Good results, and something to help you manage.
So let me back up a second before I answer that. One thing that you probably would want to do, kind of related to that, before, let me go back here. Before you actually deploy your new model, is you probably want to do a sanity check. You know, we looked at earlier, you do the test data and you say, We went from 92% accurate to 96% accurate. That's not always the case. You don't always get better. So you probably want to have a sanity check before you deploy to say, hey, how good is my model? And sometimes you can have a dip, and then in which case you would not deploy it. Maybe you would alert a human to be like, hey, someone go look at this data. Like, why did we get worse? Is it because we have some weird anomaly in the data? Is it because we tweaked our machine learning algorithm and it just doesn't work as well in the new data set? And generally speaking, that is a data scientist problem to say like, okay, why did we get better? Why do we get worse? So yeah, you would want to actually probably have a check there, or maybe even a manual, like have a human just look at it before you actually push it forward. This is all automated, but yeah, you probably would want to check it. So then now to your question of, are there tools to help like with that data? Yeah, I don't know. I mean, we have a tool in cloud called Cloud Data Prep, which helps you like clean up your data. Sarah, do you have any thought on that? I'm gonna put you on the spot. Okay, yeah. So we have a tool. I'm not like super familiar with it, but it's called Data Prep, and it's essentially like helps with like the analysis and sanitization of data. So yeah, you might check that out. But I can get you a more satisfying answer, other than hire a PhD in machine learning, which also would work.
It ends up you always have to have somebody who can make the final decision about the data being good.
Right. Yeah.
The result of the inference being good.
Yeah.
Again, massively intensive work.
Yeah, that's where you see that machine learning is still there's a lot of art to the science still of just having having data scientists who have a sense of statistics and like what are the business needs and doing all that modeling of like, it's not always that easy to just get 92% versus 96%. Like there can be some complexities there. So, yeah. Any other questions? Yep.
Do the tools support multiple input channels, so detecting not just with images but with sound?
So you would have to do, so the question is, can you have something check sound or images? So those would have to be like two completely separate models that you would train against, and it would just be depending on, so you would just check, am I checking sound, use this model, am I checking images? I don't think it would be a good idea to try and make like a general purpose ML. Like you wanna have like fairly focused data just so you can get a better prediction result. Yeah. And to that end, if you're doing things like analyzing sound, like text-to-speech, for example, or image detection, you don't have to start from scratch. TensorFlow is a super massively popular open source project, so there are a ton of getting started with X tutorials and code samples on GitHub. And also like example data sets to get playing with. So like ImageNet for doing image detection is super popular. And there's just a ton of examples of like, okay, you don't start from scratch. Like someone has already solved, honestly, probably a lot of the same ML problems you have solved, so you can find these on GitHub and online, and then just sort of put your data into it. Again, going back to the knowledge of ML, it's not quite as plug and play as we would hope. Maybe with AutoML, if you're doing images, but you do need to have a little bit. It's getting easier, but you still have to have some ML like instincts and depth of knowledge if you really want to have like a high quality production level service. So. Any other questions? Yes? Great question. So a thing that I didn't mention is that you can't just dump a bunch of images, because like, how does it know a 7 is a 7? So you actually have to have labeled data in this case. So it's really sophisticated. I just uploaded all the 7s into a directory called 7. And I uploaded all the 8s into a directory called 8. And just when it read it in, it was like, what directory is this in? Okay, right. And so, yeah, exactly. So in a more complex scenario, you would have metadata associated with each file that had like, it's not just what is the name of the file, although, I mean, that works too. So when you do the training, and I guess that's actually an important point to make, when you do the training, you have to know the answers to the data that you're training on, generally speaking, at least for this approach. Like, there are ways you can have it sort of infer a lot of this, but not for this example. You have to actually label the data when you train it. So you train on known data, and then you test on known data, and then you predict on the unknown data. So, yeah. Yeah, I just looked at the directory. Yeah. Right. So I think let me answer sort of two parts of that, or there's two answers. One is how do you get a better model generally? The presupposition here is that the more data, the better your model is going to be, which is generally true, but not always. Because then there's also the other axis of your actual machine learning code, like your TensorFlow code that you can be improving and iterating on. And this isn't really addressed that. That's more of like the data scientist thing that's like playing with data on their laptop. And so for example, I talked about the accuracy score, testing it on some data that you know the answer to that the model doesn't, to see how well it's doing. And ideally, that just continues to go up. But if it takes a big dip, or it's stagnating, no matter how much more data you give it, you can't seem to get any better, that's when you maybe need to revisit your actual TensorFlow ML code and say like, okay, I need to like choose a different kind of classifier, or I need to apply some other like ML optimizations or whatever to it. So does that sort of answer your question? So in this demo, the presupposition is the more data you give it, the better it's going to get, which again is generally true. Yes, so the question is, what if it sees something that it doesn't recognize? And the short answer is, it will always think it's something. What you get back is like a list of categories. So in this case, 0 through 9, the digits. There is a 100% total probability summed in there. Does that make sense? Like, it might be 100, I mean, well, not 100, maybe 30% sure it's a 2, and 40% sure it's a 5, and whatever. Like, it's all the percentages, confidences, if you will, are gonna add up to 100, basically. Like, it's going to think, it knows that this is its universe. So if it sees something that is super weird, it's just gonna take its best guess. So there's no, at least in this setup, there's no real way to sort of throw the red flag, and that's where you have to have like, your test data needs to be good and say like, I know there's these weird data things that I'm seeing, like a human is seeing, that I can flag and then incorporate in my test data and just see how it starts to do on that. And that's more of like a human job. Yeah. So again, like when I put in a 7, it thought it was a 0. A 7, I don't know, 2 maybe would be the closest like human judgment digit. And we basically just pick like the highest confidence level, which actually, I don't know, I can show you like the actual confidence levels for that digit. So you can see that it just buckets all of them. Because again, it thinks it knows everything that exists in the universe. Where am I? Sorry, 1 second. I will show you what the categorization looks like. Cloud function, predict image. Let me make this a little bit bigger. So here you can see, oh, well, okay, I forgot we rounded it. But realistically, these numbers would be decimals summing to 1. So these are all the, oh no, sorry, I'm in the wrong row. Yeah, but still. So these are all the classes. Sorry, it's just a log file, so it's not beautifully formatted. But here we go, this is a little bit better. So you can see of that 7, it didn't think it was anything except a 7. But the reality is it wasn't 0, 0, 0, 0, 0, 100, 0. It was like probably something more nuanced. Let me try it on the one that it actually got wrong, which I think was this one. Yeah, it's just because of the rounding. And I think we tried to get a little bit more granularity, but for the demo, it wasn't that useful. But anyway, does that answer your question? Yeah. It's a total data game. Any other questions? All right, well, that is all I have, and I do have Cloud Function stickers if you want, so thank you. bet. Thanks. Am I stopped? I just want to get out of this leave meeting. Cool. Yeah, sure.